It's about the stochastic quasi-geostrophic equation. And this is a joint work with Professor Okana and Xiangchen. And this is a reference of my talk, which can be found on the website of Bielefeld University. And here is the outline of my talk. In the first part, I will introduce the stochastic quasi-geostrophic equation. The second part is about the existence of martingale solutions and the Markov selections for alpha belongs to 0 to 1. The third part is about the existence and uniqueness of the strong solutions in the subcritical case. That means alpha bigger than 1/2. The last two parts is about the long-time behavior of the solutions. One is about the algorithmicity, the other is about the existence of random attractors. Now let's go to the first part. Consider the two-dimensional stochastic quasi-geostrophic equation on the torus. Here U is given by this formula. We can see U is a Riesz transform of the theta, and it's a non-local operator. And by this formula, we can see the divergence of U equals 0. So this equation has a similar property as the Navier-Stokes equation. And we consider this equation on this Hilbert space, and the random perturbation given by a cylindrical Wiener process W, and the operator G here. And the dispersion term given by this minus Laplacian to the power alpha. We can see if alpha becomes smaller, the dispersion term will not strong enough and cannot control this nonlinear term. So for alpha equal to 1/2, this equation is called the critical case. And for alpha bigger than 1/2, it's called subcritical case. And for alpha smaller than 1/2, it's called supercritical case. And this equation is an important model in geophysical fluid dynamics. It models the temperature of atmosphere on the rotating sphere. And for alpha equal to 1/2, it exhibits a similar singularity as the 3D Navier-Stokes equation, so it can serve as a model for 3D Navier-Stokes equation. And in the deterministic case, this equation has been studied intensively because of its mathematical importance and its background in the geophysical fluid dynamics. In the deterministic case, global existence of weak solutions has been obtained by this PhD thesis. And later, there are many papers studying this equation in the deterministic case. One of the most remarkable results obtained by Caffarelli and Zhu gives the existence of classical solutions for alpha equal to 1/2. And also in this paper, they proved for alpha equal to 1/2, if the initial value is smooth, then the solution is smooth all times. And we will study the two-dimensional stochastic quasi-geostrophic equation on the torus for general alpha and both additive and multiplicative noise. Now let's come to the condition for the noise G here. And we will use the HS to denote the Sobolev space, and this will denote the Sobolev law. And the general condition for G is the operator from the H alpha to the L2 space, or to this Hilbert symmetry operator. And it satisfies the two conditions. First is have the linear growth with respect to theta with the L2 with respect to this L2 norm, and also strong continuity with respect to theta. This is our general condition for G. Now let's come to the second part, the existence of martingale solutions and the Markov selections for alpha belongs to 0 to 1. First, I will recall the notions of solutions. First, we call a probabilistically strong solution to the stochastic quasi-geostrophic equation. If for every probability space and the cylindrical Wiener process W, we can find an adaptive process theta such that for almost all omega it's in this space, and also this theta will satisfy this equation. Here, since the divergence of U equals 0, So this term denotes the nonlinear term. And from here, we can see this equation, this theta is a weak solution in the analytic sense. And we also have the definition for the martingale solution. That means we can find a stochastic basis and a cylindrical inner process W and also adaptive process theta, such that theta is in this space, and also this equation satisfied. From here, we can see the probabilistically strong solution is stronger than this martingale solutions. First, we can prove for alpha belongs to 0 to 1 under our general assumption for G, the existence of the martingale solutions to this stochastic quasi-geostrophic equation. And to prove this result, we use standard method, just a Galerkin approximation, and benefit a lot from this paper. And recently, for alpha bigger than 1 over 2, and even can equal to 1 over 2, we can obtain the existence of the martingale solution, even if the noise is no need to be trace class, which also provide a solution to the Fock-Planck equation, as mentioned yesterday by Professor Ockner. To get the uniqueness of the solution, we need to do better regularity estimate of the solution. So here we do the LP norm estimate of the solution. So for alpha belongs to 0 to 1, under our general assumption for G, we also assume G satisfies the LP linear growth condition with respect to theta, and also satisfies this LP Lipschitz condition with respect to theta. Then we can find a martingale solution to this stochastic quasi-geostrophic equation. And moreover, if theta, if the initial value is in this LP space, then our solution will be in the LP space and satisfy this estimate. To obtain this kind of estimate, we use Krylov's LP Ito formula. Since we need to do this LP norm estimate, we can't use the Galerkin approximation. So here we use a convolutional approximation to obtain this kind of estimate. And in general, we can obtain, if we don't have the uniqueness of the solution, but we can still do the Markov selections. That means for alpha belongs to 0 to 1, under our general assumption for G, we can find a Markov family such P theta 0, such that this P theta 0 is the martingale solutions to our equation, and this P theta 0 satisfies the Markov property. To prove this result, we use the abstract result in this Gordis and Rockner and Shitten-Zhang's paper. This result. So let's come to the third part, the existence and uniqueness of the probabilistically strong solution in the subcritical case. Assume for alpha bigger than 1 over 2, if G satisfies our general condition for our general condition, and also satisfy the LP linear growth condition and also LP Lipschitz condition with respect to the LP norm. Here P will depend on this alpha here belongs to this space, and also G will satisfy this Lipschitz condition with respect to this H to the power minus 1 over 2 norm. Then we can prove the pathwise uniqueness if the solution satisfies the LP norm estimate. By this and the Yamada-Watanabe theorem, we can prove if theta 0 is in LP space, we can obtain a pathwise unique probabilistically strong solution to our equation. And moreover, this solution will satisfy this LP norm estimate. For alpha equal to 1 over 2, if the noise is a special kind of noise, just the real linear multiplicative noise, we have the similar kind of result as this one. But in general, we can't get a better estimate for, we can't get the uniqueness result for alpha equal to 1 over 2, even if the noise is additive noise. And here, for alpha bigger than 1 over 2, since we have this unique probabilistically strong solution theta. So we can prove theta can form a macro process by using the Yamato-Watanabe theorem. So we can define a semigroup PT by defining the distribution of the theta and time t. Now we want to study the long-time behavior of the semigroup PT. So first, we want to assume the noise is non-degenerate and can be written in this way. So under this condition, we can say all the assumptions above are satisfied. So under this condition, the solution theta will form a macro process, and we also have a semigroup PT. And for alpha bigger than 2/3, we can prove the strong failure property of the semigroup PT. And here, for alpha bigger than, the reason for alpha should be bigger than 2/3 is because under this assumption for G, the best regularity for the associated OU process Z has a path in this space. But to prove the strong failure property, we do the gradient estimate of the semigroup and use the Bismuth-Eversey-Lee formula. But it requires Z is in this space. So we need this one should be bigger than this one. As a result, alpha should be bigger than 2/3. If we change the value of S to make this OU process has better regularity here, but the Bismuth-Eversey-Lee formula also requires Z has this property. So we should alpha also bigger than 2/3. And we also study the associated chromography equation want to prove the strong failure property of the solutions of the semigroup PT. But there's no better result than this alpha bigger than 2/3 when the noise in this case. And moreover, for alpha bigger than 2/3, under this assumption, we can prove the existence of the invariant Mayer on the HS space by using Krylov and Borger-Liubov's method. And moreover, this semigroup PT is HS strong failure and irreducible. That means the PT has positive mass on every ball in the HS space. Then we can obtain this PT is strongly mixing. That means the PT will convergence to this nu under the total variational norm. And to prove this result, we benefit a lot from this paper. And just consider the semigroup for the cutoff equation and prove the cutoff semigroup has a strong failure property. And moreover, we can have this exponential convergence result. That means this PT will convergence to exponentially fast. And to prove this result, we also use an abstract result for the exponential convergence in this paper. And just to find a suitable Lyapunov function for our equation. And here we choose the LP norm as the Lyapunov function and can prove this exponential convergence result. And later we want to know whether this kind of algorithmic result still hold when alpha becomes smaller and the noise becomes less. And recently we can prove for alpha bigger than 1/2, if for G we can find a small g such that it's equals Pn. Here Pn is the projection onto space spanned by the first n eigenbasis of Laplacian operator. Then for this n is large enough, then we can obtain the semigroup PT is the asymptotically strong failure. And moreover, we can obtain the zero is in the support of every invariant Mayer. So we can obtain the uniqueness of the invariant Mayer mu for this semigroup here. To prove this asymptotically strong failure property, here we use the coupling method to deduce this kind of estimate. Here, this theta 1 and theta 2 is the coupling of our solutions from two different kind of initial starting point, theta 0, 1 and theta 0, 2. Then by obtaining this kind of estimate, and we can choose a suitable norm, and then we can obtain the asymptotically strong failure property. We can obtain the uniqueness of this invariant layer for this semigroup PT. And we also have another method to study the non-time behavior of the solutions. Here we want to study the existence of the random attractors for the alpha bigger than 1 over 2. And consider, first I will record the notions of the about the random attractors. Consider this VT is a family of Mayer preserving transformations on a probability space such that this Mayer is Mayerable, and when times equals 0, its identity, and also satisfy this property. Then we call this space is a dynamic system, and a random dynamic system on this space is a Mayerable map phi, such that when time equals 0, its identity on X, and also satisfy this co-cycle property for every Ts belongs R, and every omega belongs for all omega. This equation holds. So if we define phi as the solution of an SPD with the initial value X as this phi here, even if the solution has even if this SPD have a pathwise uniqueness result, we can't conclude this co-cycle property holds for each omega. So to prove this result, we need to study our equation omega y's and to conclude it. And moreover, if phi is continuous with respect to this X here, we call it a continuous random dynamic system. And for our equation for alpha bigger than 1 over 2, we can obtain the solution for this stochastic quasi-geostrophic equation. Can form a continuous random dynamic system on the H1 space if the noise is driven by if the noise is additive noise. And moreover, I will also recall some notions about the random attractors. First, consider A and B are the random sets, and A is said to absorb B. If we can find a TB which depends on omega, and if the initial value is in B, and after this, and starting from time minus t, then after some time t it will goes into A, then we call A is absorb B here. And A is said to attract B. That means A will attract all the initial values starting from B at time minus infinity. And we also have this notion of a random attractor. That means it's a compact random set A, and A is the environment, and also attract all deterministic bounded sets in this X here. And also the following proposition gives a criteria for the existence of a random attractor. That means if for a random dynamic system, we can find a compact random set absorbing every deterministic bounded set, then we can construct a random attractor. So here, consider our stochastic quasi-geostrophic equation with additive noise. Then we can prove the random dynamic system has a compact random attractor here. And we also have a similar result for this finite dimensional linear multiplicative noise. And also this large deviation principle result for this stochastic quasi-geostrophic equation in the subcritical case has also obtained by William, Professor Rockner, and Xiangchan. And here is the reference. That's all.
Thank you very much. We have lots of time for questions. Noise.
What's the reason for this particular type of the noise? The G in this quasi-geostrophic equation. Is there a particular type to model the noise that way? Not a reason for that, or a modeling reason, or?
I think we just consider in general consider just general consider the noise and study this equation.
What do you think is particular?
I mean, this G, this particular kind of multiplication of the noise. What was the reason to look at this?
This is the standard. It's sigma applied to the solution dWt. It's the standard noise that we. And this is in a sense standard noise, because if you think of the drift being random depending on the noise, and you do a Taylor expansion up to first order, you get exactly this plus sigma of xt. Here we do here it was g of theta t dWt. That is sort of the first order approximation to a vector field that gives you the ODE, if you like, up to first order by Taylor. Then you get automatically this form of equation. And since we are on a linear space, this is sort of natural to do.
Further comments or questions? No, sorry.
For alpha equal 1 alpha, could you summarize the existence of martingale solution?
Yeah, we have the existence of martingale solutions. It belongs to 0 to 1. We have the
This is for every alpha.
Yeah, and also the Markov selections. And
Also the Markov selections.
And we also have this kind of result for long-trace class noise.
So let us thank the speaker again.